design of this maybe in the left. Now, if and
Hello students, welcome to my YouTube channel VRacademy. We are here to discuss the digital electronics, and today's topic of discussion is JK flip-flop. We have already completed the SR flip-flop and D flip-flop, and we are following a particular pattern in order to understand the operation of any kind of flip-flop. So here, in order to understand the JK flip-flop, we'll be going for the definition part first, then we'll be going for the Boolean expression, then operation, then truth table, and then characteristic table, characteristic equation, excitation table, and finally the state diagram. We are following that pattern because everything is dependent on the one to other. If you know about the definition, you will be able to go for design. If you know the design, you will be able to go for Boolean expression and all. So let us start. So JK flip-flop was designed by scientist Jack Kilby. Hence the name is given as JK flip-flop because it is, it is not having any kind of relevance as it was in the case of SR flip-flop. In case of SR flip-flop, we were having the relevant of the name, that is S stands for set, R stands for reset. But because it has been invented by Jack Kilby, the J and K of first of its name is being utilized as the input to this flip-flop. Basically, it has been designed in order to resolve the problem that was occurring in case of SR flip-flop. In SR flip-flop, when we are having S equals to R is equals to 1, at that time we were getting the output to be a invalid one. I mean that we are getting the same value for uncomplemented output as well as complemented output, which was not be considered as the usual output. So therefore, in order to resolve that, what Jack and Kilby has done, that he has given that if the value of J is equals to K is equals to 1, at that time we are getting the complement, or you can say the toggle state as the output. Now coming to the design, I have already said you that all the flip-flops are getting designed with the help of SR flip-flop. Now how it is getting designed? A JK flip-flop can be designed with the help of SR flip-flop. Firstly, you need to draw a SR flip-flop. The only change that you have to make is to connect the Q bar terminal to the input of S flip-flop, or you can say input to the NAND gate where S has been connected. Similarly, you have to make a connection of Q to the NAND gate where R has been connected, and after that, in place of S and R, you will be able to write J and K, and that will be serving as the input. Now once you are done with this, you will go for derivation of the Boolean expression. The first expression you need to find out for X. I have just considered the output of this first gate. I am telling that one as G1, this one as G2, this one as G3, and this one as Z4. So the output of G1 is X, output of G2 is Y, and G3 and G4 will have the output Q and Q bar respectively. Now using the Boolean expression, normal Boolean expression, we will be able to find out the value of X. X is nothing but it is you will have Q bar, J, and clock. The complement of that one will be the answer to that. Similarly for Y, it is K, Q, and clock. The complement of that with AND gate is your Y. So after using De Morgan's, we have got X value as clock bar, J bar, and Q. Y is equals to clock bar plus K bar plus Q bar. Now we know that this operation will be started only if the K clock value is equal to 1. So put up the value of clock equals to 1, you will be getting X equals to J bar plus Q and Y equals to K bar plus Q bar. Once you have got that, you have to go for the output, that is Q and Q bar plus. So we are getting the value of Q bar plus and Q plus, and final output that we were getting after solving all those equations, we are getting that one as J bar plus Q whole bar plus Q. Similarly, we are getting Q bar plus equals to K bar plus Q bar whole bar plus Q bar. Now this is very easy. You can have the analysis. It is nothing but X plus Q bar, X dot Q bar whole bar. And if you are solving that, you will get this answer. Similarly, Y, and from here you will be getting Q, Y dot Q whole bar. And if you are solving that, you will be getting this answer. Now coming to the operation part, we have already taken clock equals to 1. We'll keep J and K equals to 0. Now if you will put J is equals to 0 and K is equals to 0, you will be finding out this value comes out to be 1 plus Q. 1 plus anything is 1. So bar of that one will be 0 and you will be getting Q. Similarly, if you are keeping K equals to 0, K bar is equals to 1. 1 plus anything is 1 and bar of that one will be 0. So you will be getting Q bar, and hence this condition is termed as no change. Similarly, if you are keeping j is equals to 0 and k is equals to 1, you will be getting, if you are keeping j is equals to 0, this is 1, 1 plus anything is 1, 1 complement is 0, you will be getting q, and from here you will be getting k has been taken as 1, so 1 complement is 0, 0 plus anything is same thing, so that is q bar, and q double bar will be equals to q plus q bar will be giving you 1, so that means q bar plus is equal to 1, and since right now we have got q bar plus 1 equals to 1, the q value will be equals to 0, and that condition will be called as your reset. This is the reset condition. After getting the reset condition, the next is j is equals to 1 and k is equals to 0. Go on putting up the values, and you will be getting q equals to 1 and q bar equals to q bar, which is nothing but the complement of q. We have got the value of q equals to 1, and therefore the complement of that one will be 0, and this condition will be serving as set condition. Now you can clearly visualize we don't have any change, any alteration in the operation of JK flip-flop with SR flip-flop. We are getting same thing, no change, reset and set. The only change that is occurring, it is occurring in the case 4, if j is equals to k is equals to 1. Now we cannot have any kind of analysis, Boolean analysis, if we are taking j is equals to 1, k is equals to 1, and it is difficult to get the value of that one as toggle, because when we are going for Boolean expression analysis, it is not a dynamic you can say analysis, it is a static analysis in which we cannot have the values of, or we cannot have the previous value coming as the output or coming as the input to your device. So in order to understand this state, you need to go for normal analysis method. You need to take this value as 0, this value as 1, or this value as 0, and then you have to go for keeping the value of j equals to 1, k equals to 1, and clock equals to 1. And if you will go for a normal analysis, you will be finding out that this q value will come out to be 0 and this q bar value will be coming out to be 1. That states that whatever value you have kept previously, it is coming as the complement of that one. That means it is nothing but q bar and this will be q. So for that reason, I have written here q will be equals to q bar and q bar equals to q. And this condition is described as toggle state. If you are facing any problem regarding this, you can come up with your suggestions in the chat box. I'll be giving a special class for that one. So this is the case. If j is equals to 1, k is equals to 1, q will be equals to q bar and q bar will be equals to q. And that state will be described as toggle state. Now once we are done with the operation, we know that the next part will be its truth table. And writing the truth table after having that operation is very easy. We'll go for clock, j, k, q, q bar. When clock is down, no operation will occur. If clock is high, we'll have 4 combinations, 0011, 0101. For a first 3 condition will be similar to your SR flip-flop. The last change or the last state will have a toggle state, means we'll be having a change, that is we'll be getting q bar at a place of. After having the truth table, next we'll be going for the characteristics table. I have already stated that characteristic table is nothing but it is a table that consists of present state and the inputs of the flip-flop along with the respective next state as the output. So what we will do, we'll take the present state qn, we'll take the inputs j and k, and from this we'll try to derive the value of qn plus 1. Now if we know these 3 as the input, how many combinations are possible? Total number of combination possibles are 8. So we are taking 4 zeros, then 4 ones, 0011, 0011, and then 0101, 0101. Now once we have got this, we have to look for how we will get the output, that is qn plus 1. So when it is 0, 0, we know that from the truth table, no change will occur, or you can say the last state is the condition. So 0, 0 means no change, means whatever value is in qn, that same will be appearing in qn plus 1. 0, 1 is reset, therefore 0, 1, 0 is set, therefore 1, 1, 1 is complement of the last state or toggle state. So 1, 0 will be converted to 1. Similarly, 0, 0 is we are having the last state we are having 1, so we have written it as 1. 0, 1 is reset, 1, 0 is set. In 1, 1, we are once again have the toggle state or the complement of the last state. So the complement of 1 is 0, so we have put up it as 0. Now once we have got this is the characteristics table for your JK flip-flop. Now next we'll be going for characteristic equation. Now I have already defined it in the previous flip-flop design. It is a Boolean expression that is the equation of next state in terms of present state and input of the flip-flop. And how to be derived, how we'll be able to derive it? You need to go for a K-map of 3 variable, because we are having Qn, J, K as the variable. So here we are taking, on the row side we are taking Qn, on the column side we are taking Jk. So this one is Qn bar Qn, J bar K bar, J bar K, Jk, Jk bar. Put up the values as 1 which are present in the Qn plus 1 in the K-map. So just have the counting of this number to get the mean terms. 0, 1, 2. So 2 we are having 1, 3 we are having 1, 4 we are having 1, and 6 we are having 1. So we are getting two you can say pairs. This one is one pair and this one is one pair. So the answer of Qn plus 1 will be the solution to these two pairs. So what is the name of this pair? If I am telling this one as the first pair, what is the name of this? Qn bar is from this side as common, and from here we are getting J as common. So I have written Qn bar J. Similarly for the second, this is the second pair. So from here Qn is the common thing, and from these two we can see that K bar is common. So I have written it as K bar Qn. So this is your expression for characteristic equation for JK flip-flop. Next we will be going for excitation table. Now excitation table, I have already said you that it is a table that consists of present state, next state serving as the input, and with the help of the values that are present in present state and next state, we are determining the response that is input to the flip-flop. So we have kept it as Qn present state, Qn plus 1 next state, and we have gone for the combination, that is 0011 0101. Now by visualizing this characteristic table, we'll be able to write it. So you can see that what is the first state is first present state is 0, next state is 0. So in this table where you are getting it, these are the first two conditions where we are getting 0 as the present state, 0 as the next state, and at that time J is fixed as 0 but K is variable. That is why I have written 0 cross. Next 0 1. So you can see that this is 0 and this one is 1. No, and this is also 0, this is also 1. But if we are looking forward, is a present state as 0, next state as 1, you can see that J is fixed as 1 but K is variable. So that is why I have written J is fixed as 1 and K is variable. Similarly, after that we'll go for 1 0. You can see that this is 1 0 and this one is also 1 0. In these two cases, you can clearly see that K value remains constant as 1, but J value changes from 0 to 1. That is why I have put a cross at J, but K value is fixed as 1, so I have written it as 1. The last one is 1 1. So you can see this and you can see this. Here in 1 1 case, J is changing from 0 to 1, but K is remain fixed on 0. So I have fixed K equals to 0 and J is not known. That is why we have put a cross. So this is about the excitation table. The last one of the explanation is state diagram. I have already said you it is a pictorial representation of the change of the states and showing all the transition with the help of arrows. So if we are having one flip-flop, we'll have two states, 0 and 1. So I have kept it as 0, I have kept it as 1. After keeping that one, just see the excitation table and go on filling it out. So when we are jumping from 0 to 0, at that time JK value is 0x. So 0 to 0, 0 to 0, JK value is 0x. When we are jumping from 0 to 1, at that time JK value is 1x. So 0 to 1, 1x. Then 1 to 0, if I am coming back from 1 to 0, we are having cross 1. So we are getting cross 1. And if we are from remaining at 1 to 1, we are having cross 0. So this is the value. So this is all about the state diagram. Now we have already understood that how we are making the transition just by knowing the definition of the JK flip-flop. We are able to design it. I mean, once we know that what exactly JK flip-flop is and why it has been designed, after that we are able to design its diagram. Once the design is done, after that we are going for Boolean expression. Then we are going for, with the help of Boolean expression, we are going for truth table. Truth table will give us characteristic table. Characteristic table will give characteristic equation. And we can derive the excitation table with the help of characteristic table, and state diagram can be derived from excitation table. So all of them are interlinked, and if you have understood it finally, that's fine. If you have got any problem, come up with that in the comment box. It will be highly appreciated. Thank you for joining. We'll be discussing about the next flip-flop in the next class. Thank you.